This is one application. Right now, it is live on a real domain. It scales itself from 2 copies to 20 when traffic spikes. It heals itself when something crashes. It runs in 2 regions, so it survives an outage. Every request is traced, and it is locked down so tight that if I try to attack it, AWS pages me. By the end of this one video, you will build all of it from a single empty folder on the real AWS console with me. No prior container experience needed. This is the complete course, 1 video, 10 levels. Bookmark the chapters in the description, and let's go. Here is the whole journey. Chapter 1. We deploy a real container and beat the 4 settings that break almost every first deployment. Then we make it bulletproof, then it scales on real traffic, then we make it private and delete a surprise bill, then we harden it, then we cut the cost by 70%, then we ship it automatically on every Git push, then we learn to debug it in production, then we go multi-region. And finally, we make it truly production-ready with backups, compliance, and chaos testing. Each chapter starts with the live payoff, then we build it. Don't just watch, build it with me. Chapter 1. The goal, this exact page, live, served by a container on AWS Fargate behind a load balancer. No server I started, no machine I keep on. By the end of this chapter, you'll deploy any app the same way. But first, the one idea everything rests on, what is a container? Imagine you cook a dish perfectly at home, but in a friend's kitchen it tastes wrong. Different stove, different ingredients. Software has the same problem. It works on my machine but breaks on the server. A container fixes this. It is a sealed lunchbox that holds your app and everything it needs, the exact code, the exact tools, the exact versions. That sealed box runs the same way everywhere, your laptop, my laptop, the cloud. Docker is the tool that makes these boxes. You write one small file, a Docker file, the recipe, start from this base, copy my code in, run it like this. One command, docker build, packs everything into a sealed unit called an image. Quick but important, an image is the box on a shelf. A container is that box opened and running. One image, many identical containers. Here's our tiny app and its Docker file. Before I touch the cloud, I do the thing most tutorials skip, I test it locally. Docker build, then docker run, -p80:80, and I open localhost. There it is, working on my machine. That 30 seconds saves you from debugging in the cloud what was already broken on your laptop. Now, where does this image live so the cloud can use it? You need a registry, a private shelf for your images. On AWS, that's ECR, the Elastic Container Registry. I create a repository, log docker in, tag the image with the shelf's address, and docker push. Now the image sits safely in ECR, ready for AWS to pull. Next word, serverless, and it's badly named. Serverless does not mean no servers. The servers are there, you just never see them, never patch them, never pay for them sitting idle. You hand AWS your container and say run this, it finds a machine, runs it, and bills you for the seconds it runs. That's Fargate, serverless containers, no fleet to babysit. To run containers, we need a cluster, just a named home where they live. With Fargate, the cluster has 0 servers inside it for you to manage. It's a label that says, my stuff runs here. One click, create cluster, done. Now the recipe for one container, the task definition. It answers, which image, how much CPU and memory, which port. Think of it as the job card for one container. But there are 2 blanks on this job card that confuse almost everyone, 2 different permission slips, and getting them mixed up is the #1 reason a first deploy fails. This is the most important 90 seconds of the chapter, the 2 IAM roles. A role is a permission slip, a badge that says you're allowed to do this. The first is the execution role. It is not for your app, it's for the AWS agent that sets your container up. It lets AWS pull your image from ECR and write your logs. Think of it as the crane operator's badge, the crane that lifts your container into place. Miss this badge and you get the classic cannot pull container error. The second is the task role, completely different. The task role is your app's own badge, what your running code may touch, like reading a file from S3. The crane operator's badge gets the box delivered. The cargo's own customs permit says what that cargo may do once unpacked. Say it with me, execution role delivers the container, task role is what the app inside may do. Get these straight and most container pain just vanishes. Now we run it, and on purpose, I'm going to let it break, because the 4 settings that fail here are the ones nobody warns you about. We create a service, ask for 2 copies, and we need the world to reach them through one stable front door, the application load balancer. Watch what happens when I wire it up the way a beginner would. Trap 1. I create the target group and leave it as instance type. Look, the tasks never go healthy, the load balancer refuses to route, and the logs tell me nothing. On Fargate, the target group must be IP type, not instance. People lose hours here. I fix it to IP, and the targets start passing. Trap 2. The tasks won't even start, stuck in pending, cannot pull image. The task has no public path to reach ECR. I flip assign public IP to enabled, and now it can pull. Trap 3. The health check is pointed at the default / on the wrong port, so healthy tasks look sick. I point it at our real health path on the container port, and they go green. Trap 4. The quietest one. Everything looks healthy, but the page times out. The container security group is a guest list, and by default, the door is shut. The fix is one rule: allow port 80, but only from the load balancer security group, not from the whole internet. I add it and watch. The gateway timeout turns into our live page. 4 settings, and they break almost every first deploy. Moment of truth. I open the address, and there it is, our app, live, on Fargate, behind a real load balancer. Refresh, and the container host changes. That's the balancer spreading you across both copies. You just deployed a containerized app the professional way, and you saw exactly what breaks and how to fix it. Before we move on, the rule that keeps your bill at 0, always be ready to tear down, we'll do the full cleanup at the very end. Chapter 1, done. Next, we make this thing unbreakable. Chapter 2, our app is live, but live isn't the same as reliable. So I'm going to do something scary. I'm going to deploy a broken version on purpose. And you'll watch AWS catch it and roll back by itself, while real users never see a single error. Let's make this thing unbreakable. First, 2 kinds of health check, and people confuse them. The container health check runs inside the box, your app checking itself over localhost. The load balancer health check is outside, the balancer poking your app to decide whether to send it traffic. A task can pass one and fail the other. You want both, because they catch different failures. Now the safety net for deploys. There are actually 2, and they catch opposite problems. The deployment circuit breaker watches for containers that never start, a crash loop, a bad image. But what if the container starts perfectly and then serves errors to every user? The circuit breaker can't see that. For that, you wire a CloudWatch alarm on your error rate and roll back on the alarm. Enable both. They cover orthogonal failures. Watch. I turn on the circuit breaker with rollback, then I deploy an image I know is broken. The new tasks try to start, they fail, AWS counts the failures, declares the deployment failed, and automatically rolls back to the last good version. I never touched a thing. The site stayed up the entire time. But a deploy that works can still drop requests if you're careless. When AWS stops an old task, it sends a polite signal, sigterm, then waits, then forces it off. If your app ignores sigterm, it gets killed mid-request. So your app must catch sigterm and finish in-flight work, and you set a stop timeout that gives it room. Just as important, the load balancer must stop sending new requests before that, the deregistration delay, and it has to be long enough for your slowest request to finish. One ordering rule that bites everyone: your app's keep alive timeout must be longer than the load balancer's idle timeout, or the balancer reuses a connection the app just closed and the user gets a 502. Set the app higher than the balancer. Get this chain right: deregister drain, stop, and a rolling deploy is truly 0 downtime. Last reliability rule: run a service, not a standalone task. Only a service replaces a task when it crashes, when its availability zone fails, or when AWS retires the platform underneath it. A lone task that dies just stays dead. Proof: here's a curl loop hammering the site while I do a full rolling deploy, and the success counter never drops. Chapter 2, done. Now let's make it scale. Chapter 3, 2 copies is fine until a traffic spike. So let's make the app grow and shrink by itself. The payoff: watch this, I'll throw a load test at it, and the number of running containers climbs from 2 toward 20, the response time stays flat, and when the traffic stops, it drains back to 2. And it costs cents. First, the gotcha that makes people think scaling is broken. The scaling isn't built into the service. You have to register the service as a scalable target first, with a minimum and a maximum. Skip that one step and nothing scales, ever. So we register it, min 2, max 20. Now, what do we scale on? Most tutorials scale on CPU, and for a web app that's often wrong. Your site can be drowning in requests while the CPU looks calm. The better signal is requests per target. The load balancer literally counts requests per container. We set a target tracking policy, keep it around 1,000 requests per task, and AWS adds and removes containers like a thermostat. There are other modes for other needs. Step scaling reacts in big jumps to sudden spikes. Scheduled scaling pre-warms before a known 9 a.m. rush, because reactive scaling reacts a little too late for a predictable wave. And you can scale to 0 for a non-production app, so it costs nothing while idle. 2 knobs to set sanely. Cooldowns stop it from flapping, adding and removing tasks every minute. And the maximum is your safety rail. It caps both a runaway bill and a runaway scale during an attack. Also, scaling acts on the tasks actually running, not the number you wished for, which is why it won't balloon insanely when capacity is tight. While we're here, a free win. Fargate bills you per vCPU second, so 2 things matter. 1, you can only pick valid CPU and memory pairs. Asking for more memory can force a pricier CPU tier. 2, switch the architecture to ARM, that's Graviton, 1 line in the task definition, and you get roughly 20% cheaper for the same work. Here's the load test. Requests on one axis, running tasks on the other, tracking in real time. That's elasticity. Chapter 3, done. Next, we make it private and delete a bill. Chapter 4. Right now, our containers sit in public subnets with public addresses. That works, but it's not how you run things in production, and it's quietly costing you money. The payoff for this chapter: the exact same app, fully private, no public address at all, and I'm going to delete a $30 a month charge you probably didn't know you had. Quick mental model. A VPC is your own private slice of AWS. Inside it, public subnets can reach the internet directly, private subnets cannot. For security, you want your containers and private subnets hidden. But that creates a problem. A private task still needs to pull its image from ECR and ship its logs, and with no internet path, it can't. The lazy fix is a NAT gateway, a paid box that gives private things a one-way door to the internet. It works, but it bills you per hour and per gigabyte, so every image pull and every log line quietly meters money. There's a better way. VPC endpoints. These are private on-ramps straight to AWS services, no internet, no NAT. You need a few: ECR API and ECR Docker for pulling the image, the S3 gateway endpoint, because image layers actually live in S3, CloudWatch logs for logging, and Secrets Manager for secrets. Add those, and a fully private task can pull, log, and read secrets with 0 internet route. Here's the trap I'll show you live. I add the 2 ECR endpoints but forget the S3 gateway endpoint, and the pull fails, cannot pull container. Everyone hits this. The image layers are in S3, so without that one free gateway endpoint, nothing pulls. I add it, and the task launches in a private subnet. Now I delete the NAT gateway, and the bill line disappears. While we're in the network, 2 more professional habits. Instead of writing firewall rules with IP ranges that change, you reference one security group from another. The database group allows the app group allows the load balancer group. Rules that stay correct as things scale. And know the wall. Every Fargate task takes its own network card and its own IP, so a small subnet runs out of addresses and scaling silently stalls. Give yourself room, or turn on chunking. Chapter 4, done. Now we lock it down. Chapter 5. The app is private now, but private isn't secure. So in this chapter, I'm going to attack my own container, and you'll watch AWS detect the exact command I run and raise an alert. Then we'll close every door that let it happen. This is the difference between it works and it's safe. Back to those 2 roles, but now the security view. The task role, your app's badge, should be scoped to exactly what it touches. This one bucket, this one table, never star, never full access. Because if your app is ever breached, the attacker gets exactly those permissions and nothing more. The execution role, likewise, only the specific secrets it needs to inject. Least privilege isn't paranoia, it's blast radius control. Secrets. Never put a password in a plain environment variable. Anyone with read access to the task definition can see it in clear text. Instead, you store it in Secrets Manager and reference it. AWS injects it at start time, and it never appears in the definition or the logs. Even better, Secrets Manager can rotate it automatically, so a leaked password expires on its own. harden the image itself. Turn on ECR scanning, basic catches operating system vulnerabilities, enhanced uses inspector to continuously scan your language packages too, and rechecks old images when a new vulnerability appears. In the task definition, make the root file system read, only so a compromised process can't write malware, and run as a non-root user so a break-in doesn't start with admin rights. Drop the Linux capabilities you don't use. Now the live demo. I turn on guard duty runtime monitoring, which drops a tiny managed agent beside each task. Then I use ECS exec to shell into my own running container and run a suspicious command, the kind an attacker would. Within moments, a guard duty finding appears naming the process and the command line. That's runtime defense. A static deploy has exactly 0 of. 2 finishing touches. Encrypt your logs and secrets with your own KNS key, so access is gated and auditable. And every time someone uses ECS exec to shell in, log that session, who connected, and what they ran. Wire it all to Security Hub, and it scores you against the standard benchmark automatically. Chapter 5, done. Now, let's make all of this 70% cheaper. Chapter 6. The cloud will happily charge you for every idle thing you leave running, so let's slash this bill. Here are 2 screenshots of Cost Explorer, the same workload, before and after the changes in this chapter, about 70% cheaper. Here's exactly what I changed. The biggest lever Fargate spot. AWS sells spare capacity at up to 70% off, and for anything that can tolerate an interruption, that's free money. You set a capacity provider strategy, keep a base of a few on-demand tasks for safety, then put the rest on Spot. The catch, AWS can reclaim Spot with a 2-minute warning, the same SIG term we already handle from Chapter 2, so a graceful app loses nothing. 2 more discounts that stack. Graviton, the ARM architecture, roughly 20% cheaper for the same work, 1 line in the task definition. And if you have a steady baseline, a compute savings plan commits to an hourly spend for 1 or 3 years and knocks up to half off. Spot for the bursty part, savings plan for the steady part. Now stop paying for waste. Fargate bills the size you reserve, not what you use, so right size. Compute Optimizer reads your real usage and tells you how much smaller to go. Remember those VPC endpoints from Chapter 4? They don't just add security, they kill the per gigabyte NAT charge. And notice your load balancer bills by the hour even with 0 traffic, so consolidate small services behind 1 balancer instead of 1 each. Finally, the silent compounding costs. Your logs default to being kept forever, set a retention, a week or a month, and switch chatty logs to the cheaper class. Your image registry keeps every build forever, add a lifecycle rule to expire old images. And for non-production, schedule it to scale to 0 overnight and on weekends. Tag everything by team and environment, activate those tags in billing, and now you can actually see who spends what. Here's the before and after invoice. Chapter 6, done. Now let's ship it automatically. Chapter 7. So far I've been deploying by hand. Real teams don't. The payoff, I push code to Git, and it builds, tests, and goes live by itself with 0 downtime. And if the new version is bad, it rolls back on its own. Let's build that pipeline. First, how the pipeline talks to AWS. The old way, you paste long-lived access keys into your CI, and leaked keys are one of the top ways companies get breached. The modern way is OIDC. Your pipeline assumes a role for the moment it runs, no stored keys at all. We set that up first. Now the build. On every push, the pipeline builds the image and tags it, and here's the rule. Tag it with the git commit hash, never just latest. Latest is a moving target. You can never tell what's actually running or roll back cleanly. A commit hashtag pins an exact reproducible build. We render the task definition from a template with that new image as code in version control. Then the deploy, and we level up from Chapter 1. Instead of replacing tasks in place, we do blue-green. We stand up the new version, green, alongside the old, blue, and we point a separate test listener at green so we can check it privately before any real user touches it. Then we shift production traffic over, all at once, or a slow canary, and if anything looks wrong, 1 click or an automatic alarm sends everyone back to blue. We even put a gate inside the deployment, a lifecycle hook that runs a smoke test against green and refuses to shift traffic if it fails. Watch, I push a good commit, it sails through to live. Then I push a deliberately broken commit, the smoke test fails, and the pipeline rolls it back before a single user sees it. The same image then promotes from dev to staging to production, never rebuilt, so what you tested is exactly what ships. Chapter 7, done. Next, when it breaks at 3 a.m., how to find out why. Chapter 8. Everything's automated now, but one day it will break in production, and the only thing that matters is how fast you find out why. The payoff: I'll break the app on purpose and find the exact cause in about 2 minutes without ever SSHing into anything, because on Fargate you can't, and you don't need to. Start with eyes. Turn on Container Insights and you get dashboards for CPU, memory, and task counts out of the box. Send structured logs, JSON, not plain text, so you can actually query them, and use Spiralens if you want to route them to other tools. For request flows across services, add tracing with X-ray or ADOT so you can see which hop is slow instead of guessing. Then alarms on the signals that matter, not just CPU. Watch your 500 error rate, your count of unhealthy hosts, and the gap between the tasks you want and the tasks actually running. Wire task state changes to event bridge, so a task dying can trigger an automatic response. Now the debugging itself. First, read the death note. Every stopped task has a stopped reason and an exit code. 137 usually means out of memory or a forced kill. 139 often a crash or a bad environment variable. 255 with exec format error means you built the image for the wrong chip. ARM versus x86. Learn these three and you've diagnosed half of all failures on the console alone. And the trio at the load balancer, learn to read them. 502 usually means your app closed a connection, the balancer reused, that keep alive rule from Chapter 2. 503 means no healthy targets at all. 504 means your app was too slow and the balancer gave up. 3 different problems, 3 different fixes. The power tool, ECS exec. Watch, the app is misbehaving. I run one command and I'm shelled directly into the running Fargate container. In production, no bastion, no SSH key. I check the process, spot the bad config, and the trace already told me which call was slow. 2 minutes, root cause found. That's the difference between panic and a calm fix. Chapter 8, done. Now let's make it survive a whole region going down. Chapter 9. Before we go big, the most important architecture question: should this even be ECS? The honest decision tree: app runner if you just want to run a web app and nothing more, Lambda for short driven bursts under 15 minutes, ECS with Fargate for long-running containers with minimal ops. That's us, and EKS only if you specifically need Kubernetes. Choosing wrong is the most expensive mistake a beginner makes, so I'll show you exactly when each one wins. Now, where do the containers actually run? Fargate, no servers, what we've used. The EC2 launch type when you need a specific machine, a GPU, or higher density. And the newest option, ECS managed instances, where AWS runs and patches the servers for you, but you still get GPS and privileged access, the middle ground. You tie these together with capacity providers. Our app is stateless, which is why it scaled so easily. Real apps have state, so I'll show the patterns: a shared file system with EFS for files, a managed database with RDS, and RDS proxy in front to pull connections when tasks churn. For jobs that run and finish instead of running forever, you schedule them with EventBridge Scheduler, orchestrate them with step functions, no always-on service needed. And the big one, surviving a region outage. We replicate the image to a second region, stand up the service there too, put R5-3DNS in front with health-based failover, and replicate the database with a global setup. Watch, I deliberately take down the primary region, and within seconds DNS fails traffic over to the second region, and the app stays up. That's the architecture that lets you sleep at night. Chapter 9, done. 1 chapter left, making it truly production ready. Chapter 10, the final one. The app deploys, scales, heals, and fails over. But would it survive an audit, a deleted database, and a real outage drill? It deploys is not the same as it's production ready, so let's stress it and close the last gaps almost every tutorial ignores. First, testing you can't see in a demo but can't ship without. Scan the image and generate a bill of materials so you know every package inside it. Gate your infrastructure code with policy checks before it deploys, so a misconfiguration never reaches production. And run load and soak tests to prove the auto-scaling from Chapter 3 actually holds under sustained pressure. Second, the gap this whole course quietly had until now, your data. We mounted a file system and a database, but we never protected them. Turn on a AWS backup for both, with point-in-time recovery, and store copies in a separate account so even ransomware can't reach them. Then, and this is the part people skip, actually test to restore. A backup you've never restored is just a hope. Third, compliance that runs itself. Instead of a one-time security check, use AWS config conformance packs, rules that continuously flag any task running as root, any plaintext secret, any old platform version, and report drift automatically. That's the difference between passing an audit once and staying compliant. And finally, the bravest test of all, chaos engineering. Using the fault injection service, I deliberately kill a running task and the service replaces it. Then I take out an entire availability zone and the app stays up. You don't truly have reliability until you've proven it by breaking things on purpose. If your service survives this, it's production ready. Now the habit that keeps your bill at 0, the full teardown. We scale the service to 0, delete it, delete the load balancer and its target group, the NAT is already gone, and confirm in Cost Explorer that the meter has stopped. The cluster, the roles, and the registry are free to leave. After any demo, tear it down. A forgotten load balancer is the #1 surprise on a beginner's bill. Look back at what you built. From a single folder, you deployed a container and beat the 4 traps, made it self-healing, made it scale on real traffic, made it private and killed a bill, hardened it until AWS guards it, cut the cost by 70%, shipped it automatically with safe rollbacks, learned to debug it live, spread it across regions, and proved it with chaos. That is the entire shipping port, and you now run production containers on AWS, the single most in-demand cloud skill today. If even half of this clicked, you are genuinely ahead of most working engineers. Every chapter is timestamped in the description, so come back to any level when you need it. Tell me in the comments which chapter saved you, and drop your stuck task error. I read them. If this was worth it, subscribe. It's the only way these full builds find you. I'm Vion. Now go build something and tear it down after. See you in the next one.